You've seen it, right? Technology that seems to pull poetry, code, and just unbelievable images right out of thin air. We're talking about generative AI, of course. And yeah, it really does feel like magic. But behind the curtain, there are some truly brilliant ideas at play. In this explainer, we're going to pull that curtain back and see exactly how the trick is done. I mean, we've all experienced it by now. You ask a chatbot to write an email for you, and poof, it's done. Or you type a crazy description into an image generator and get back a piece of art that would have taken a human weeks to create. This stuff is everywhere, and it's completely changing the game.
Okay, so it's one thing to see the amazing results, but it's another thing entirely to understand what's actually going on under the hood. How does a machine learn to grasp context, nuance, or even artistic style? Well, that's exactly what we're here for. Let's pop the hood and take a look.
So, at the very heart of all this modern generative AI, it really boils down to three core concepts. Think of them as the engines. First, we've got transformers, which are the masters of language. Then diffusion models, which literally create from chaos. And finally, multi-modal models, which are learning to tie it all together, to understand the world a lot more like we do. All right. First up, let's talk about the architecture that absolutely revolutionized how AI understands language, the transformer. This is the powerhouse behind models like GPT-4, and it's the reason chatbots suddenly went from clunky to convincingly human. So here's the fundamental problem that AI had to solve. Human language is just incredibly complex. It's not just a string of words. The meaning of any single word can completely change based on all the other words around it. Think about a sentence like, "The riverbank was flooded." How does an AI know we're not talking about a money bank? That's the challenge. It's all about context. The absolute genius of the transformer lies in this one key mechanism called self-attention. The best way to think about it is this. It's the model's ability to read a whole sentence at once and figure out which words are most important for understanding any other word in that sentence. In our example, self-attention is how the model instantly connects river to bank and just knows we're talking about the edge of the water. It creates this web of connections, weighing every relationship simultaneously. And this is where it gets really cool. Inside that attention mechanism, the model learns all these specialized little jobs. Some parts, for example, get really good at looking back at patterns it's seen before. So what you're seeing in this diagram is basically that process. If the model has seen A followed by B thousands of times, it learns to predict that if it sees an A again, a B is probably coming next. This is how transformers learn not just vocabulary, but the deep underlying structures of grammar, style, and even logic. And because they have this incredibly deep understanding of context, transformers are just phenomenal at a whole range of things. This is why they can generate such human-like text for chatbots. It's why they can summarize a huge article and not lose the main point, or why they can translate languages with such amazing accuracy. It all comes back to understanding those relationships. Okay, let's totally shift gears. We've talked about understanding language. Now let's talk about creating something brand new, like an image, from scratch. This is the wild world of diffusion models, and their whole approach to creation starts with, believe it or not, pure chaos. The central challenge here is almost a philosophical one. I mean, how do you teach a computer to create a picture of an astronaut riding a horse when all it has to start with is random static? It's kind of like asking a sculptor to find a perfect statue inside a block of marble they've never even seen before. Where do you even begin? Well, diffusion models solve this with this absolutely brilliant two-step process. First, you have what's called the forward process. You take a real image and you just systematically add a little bit of noise, over and over, until it's nothing but unrecognizable static. Then comes the really clever part, the reverse process. You train a model to do the exact opposite, to learn step by step how to remove that noise, gradually revealing a clear, coherent image from that starting point of pure static. And get this idea isn't just some clever programming trick. It actually has really deep roots in science. As this quote points out, the whole concept was inspired by non-equilibrium thermodynamics. The same kind of physics that describes how a drop of ink slowly spreads out or diffuses in a glass of water. So the whole takeaway is this. After watching thousands and thousands of images dissolve into noise, the model gets unbelievably good at reversing that process. It learns what a coherent image is supposed to look like at every single stage of noisiness. And because of that, it can essentially sculpt a masterpiece out of what started as random pixels. It literally learns how to undo chaos. It's amazing. Okay, so we have models that can understand language and models that can create from noise. The final piece of this incredible puzzle is bringing those different worlds together. And that is the whole goal of multimodal models. Just think about how you and I experience the world. We see a dog, we hear it bark, and we can read the word dog. For us, all of those different inputs point to the exact same concept in our brain. So for AI to get a truly deep understanding of things, it needs to do the same. It needs to connect information from text, from images, from audio, and more, all at the same time. And this slide just lays it out perfectly. A unimodal AI is a specialist. It's great with one type of data, like text or images. But a multimodal AI is a generalist. It learns to integrate multiple data types, to understand the deep relationships between text and images and audio. So how on earth does it do that? Well, the key idea is creating something called a shared semantic subspace. Now, I know that sounds super technical, but think of it like a universal map of meaning that lives inside the AI. On this map, the AI learns to place things that mean the same thing really close together, no matter what they are. So the sound of a dog barking, the text that says a furry canine, and a photo of a golden retriever all get mapped to the same neighborhood on this map. They become linked. And having this unified understanding, it is a total game changer. It closes the gap between different formats. It lets us do powerful new things like analyze a video using both what you see and what you hear. And it makes incredible things possible, like automatically writing a perfect caption for an image. Ultimately, it just gives the AI a much richer, more complete picture of the world. So, as we wrap things up here, it's pretty clear that the amazing generative AI tools we're all using today aren't the result of just one single breakthrough. No, it's about how all of these powerful ideas are coming together. So let's do a super quick recap. We've got transformers using self-attention to master the context of language. We've got diffusion models, which learn to reverse chaos to create brand new things from scratch. And we have multimodal models, which are building that unified map of meaning across all these different types of data. Look, each one of these engines is incredibly powerful on its own, but as they get combined and refined, they're creating an AI that doesn't just process data, but actually begins to understand concepts in a way that feels a lot more like how we do it. And that leaves us with a pretty fascinating question to think about. When an AI can truly start to understand our world, what in the world is it going to create next?